Now, please allow me to introduce our speaker. Benjamin Worsfold is UC Berkeley's current TY Lynn Fellow. He completed his undergraduate degree in civil engineering at the University of Costa Rica in 2015 and worked for 2 years at a local design firm. He is currently a fourth-year PhD student at UC Berkeley, working with Dr. Jack P. Mohili in the structural engineering, mechanics, and materials department. His research focuses on analytical and experimental behavior of cast in place headed anchors and headed rebar in reinforced concrete structures. Other interests include numerical analysis and finite elements analysis. He will be talking about column foundation moment connections with headed anchors, experimental tests, and analytical simulations. Now, Benjamin, if you can please turn on your microphone, your webcam, and also share your screen, the virtual stage is yours. And I'll mute myself.
Sure. So thank you so much, Emanuele. Just to double check, can you see me and see the screen as well?
Yes,
Sure.
I can see you and we can see your screen.
Okay.
Perfect. And also your pointer. Yeah.
Pointer. Okay. Perfect. So jump in if anything stops working. But yeah, thank you so much for having me. This is really an honor to be able to speak to all of you. My advisor, Professor Jack Maley, I believe, was down in Auckland last year and gave a talk to you guys. And so he was excited to hear that you had invited me to come along too. So I'd like to share a little bit about my research, the research I've been doing here at Berkeley for the last couple of years. As Emanuele said, my name is Benjamin Worsfold. I'm fourth-year PhD student here. And most of the time here, I've been working on the subject you see on the screen, column foundation moment connections with headed anchors. I'll talk a little bit about the physical experiments we've run and also some of the analytical simulations that we've been working on recently too. I had a quick check in the New Zealand code, and it looks like the way the New Zealand code deals with anchors is basically the same as the way the American code deals with anchoring to concrete problems. So I believe all my conclusions also apply to the New Zealand code as well. But jump in if anything is different. So let's get started. My presentation, I'll first talk about the physical tests that we've run here. Then I'll explain the finite element model calibrations that we've been working on, and finally some of the parametric studies. So just to make sure we're all on the same page, I'm talking about what you see on the screen, column foundation connections with cast-in-place headed anchors. So when you have your column, it has to connect to the foundation. We have to do that in some way. And cast-in-place anchors are one of the most common ways to do that. So on the picture on your right, you can see what these connections might look like. Before the concrete is cast, you have the rebar, the slab, and you have to hold the anchor in place. You might not see it in the picture, but at the base of the anchor, there has to be some kind of head, a nut, a bulb, or something, so that when you pull the anchor out, it gets stuck in the concrete. Once you pour the concrete and remove the forms, the tops of the anchors are sticking out, and then you place the column on top and you can bolt it down with some type of anchor. And this is very common construction type in the US, and I'm assuming in New Zealand as well. But even though it is very common, there isn't much consensus as to how these should be designed, which is somewhat concerning given how common these connections are. And I'm focusing mainly on the concrete portion of these connections, not so much the base plate and the wells and that sort. I'm talking about the failure of the concrete. There are multiple methods for designing these connections, and there's very little agreement as to which method should be used when designing these anchors. One of these methods is what we call the breakout equations. It's chapter 17 in the American Concrete Institute code. It also happens to be chapter 17 in the New Zealand code. Basically, if you have a moment acting on a column that's resolved by a tension compression couple, and if this tensile force is large enough, this method says that you would expect to see a failure mode where you rip out a chunk of concrete in the shape of a cone. So this failure mode is often called the concrete cone failure or the breakout cone failure mode. And we have equations calibrated to calculate the strength of these connections. But these equations tend to be very conservative, and people try not to use them. Also, if you use any of the software by some of the fabricators of anchors, like Hilti and whatnot, they use this method. But a lot of people shy away from it. They say it's very conservative, which it is, and they argue that we should be able to use other methods. Say this, number 2, Strut-and-tie models. If we load the column in the same way, we have a tensile force on the left, but in this case, we'll have a diagonal compression strut along the joint. And the argument here is if you make that strut strong enough to be able to resist these forces, then you should be fine. You shouldn't get any kind of breakout cone, and we can ignore the breakout equations completely, not even have to check them. Other engineers argue that even that's too complex. We can use this simpler version. How about we use the horizontal joint shear equations? These are just the traditional joint equations for concrete beam column joints. If you look on the left, there's a diagram of a roof joint. So the column terminates and you have beams framing in from the sides. If we flip this upside down, the argument goes, the force flow is very similar, so these equations should apply to this type of connection. We simply have to size the joint such that the horizontal joint shear is resisted, and again, we can ignore the breakout failure modes, and we don't even have to check for them. So we have 3 methods to design the same connection. That would be fine if these 3 methods gave us similar results, but they don't. There's about an order of magnitude difference between these results, and that's quite concerning, especially because it's not common that people check with these different methods. They just tend to pick one and stick with it. There's also very little data to tell us which of these methods works well for large-scale connections. Anchoring to concrete is one of those problems that doesn't scale well. So using half-scale, quarter-scale tests, whatnot, tends to not work very well at all. It tends to be very sensitive to scaling. So there's very few full-scale tests out there. So that was one of the first projects I did when I first started my work here at Berkeley. We designed and built and tested a full-scale column foundation connection. So here we have a steel column in the middle. It's anchored to the foundation with 2 anchor groups, one on each side. And we have our foundation slab along the bottom. It's 18 inches thick, and you're going to have to forgive all my crazy American units. I grew up with the metric system in Costa Rica, but I've been here for 4 years and kind of gotten used to these crazy units, about 45 centimeters or so thick. And with this specimen, we ran through these 3 design methods. How strong is this connection? How much load can we apply to this column? And here I'm showing the result from these 3 methods. So what I'm graphing in the vertical axis is the anchor, the load in the anchor group at failure. So if you look at the breakout equations, it says the anchors should fail at about 650 kilonewtons. Strut-and-tie model says that no, you should get a joint strut failure at about 110. If you decide to trust the beam column joint equations, they say no, your connection is much stronger than that. You should be able to get all the way up to about 1800 kilonewtons. So as you can see, this is quite concerning. These equations are very different, and we're trying to analyze one connection. We shouldn't have such a difference here. One thing I wanted to highlight is that what I'm showing on this graph are the median capacities. Basically, I've taken all the safety factors out from each of these methods. But there's kind of a hidden safety factor in the breakout equations that most of the equations in the code are designed to describe the 50th percentile. So you have your distribution of capacities, and our equations are calibrated to fit the 50th percentile. We apply a phi factor onto that to pull it down to some acceptable safety level. The thing is that breakout equations are not calibrated towards the 50th percentile, but towards the 5th percentile. So they're quite a bit lower, these equations. And then on top of that, you apply the corresponding phi factor. So here I'm showing in the diagram this bottom line with the times phi symbol. That's the number you would get if you run through the code equations. Each method has its own phi factor, but if you look at the breakout equations case, the force you're allowed to use by code is about something like 350 kilonewtons, when it's trying really to describe a distribution that has a median of about 650. So we're using about half of that. And that's not the case for the other methods. So from now on, I'm going to just talk about the median capacities. So taking out all of the safety factors. But I do think it's important to highlight that each method has very different safety factors. We can talk a little more about that later if you guys are interested. So what we did was test this column in the lab and see what we get. What method do you trust? Do you trust breakout equations, Strut-and-tie models, or beam column joint equations? So this is a quick video of the test. We have our foundation along the bottom, simply supported on 2 concrete blocks. We have a steel column anchored in the middle. This is trying to simulate a column and in the interior of a building, so far away from the edges of the foundation. And then we have actuators on the top of the column attached to the free end. And we're displacing the free end of the column in one direction. We have cyclic monotonic loading, and on the right-hand side, you can see the load displacement curve. So one of the first observations that we wanted to see with this test is what failure mode do we get? Each of these 3 methods describes a different failure mode: concrete cone failure, joint failure, etc. And so the first thing we looked for was what kind of failure did we get? Here on the top, you can see a cross-section of the slab, and on the bottom, I'm showing a picture of the top surface of the slab after testing, so you can see all the cracks that were highlighted there. I wanted to point out the failure cones. We did, in fact, see concrete failure cones, even though the proponents of the Strut-and-tie models say that these failure cones don't happen for this geometry. We did see them. So as we were loading in one direction, we saw one cone. The cone originates at the head, and as it shoots up towards the surface, when it intersects the surface, we get a more or less circular pattern. So we saw that crack on one side. And then we loaded in the other direction, and we also got our breakout failure cone. So that should maybe give you an idea of what method might be the most appropriate for designing these connections. If we saw a breakout failure, maybe the breakout equations would be the best. So if I bring back this table or this graph I showed you before with the load that each method predicted, I can add 2 columns to add in the measured loads. So even though we just had one specimen, we had 2 anchor groups, east and west, so we have 2 failure loads. If we take the average of these 2 as 100%, the breakout equations, even with all the safety factors taken out, only reach 58% of what was experimentally observed. So these breakout equations still seem to be conservative, even after taking out some of these, the additional safety factors in these methods. Strut-and-tie model is way too low. It really only serves as a lower bound solution. So it tells us that the Strut-and-tie model tells us that our connection will resist more than 107 kilonewtons, which is correct, but not very useful for design. And thirdly, the beam column joint equations don't seem to be a safe alternative. They over-predicted the strength by about 60%. So because of this type of failure, we saw breakout type failure. It seems like these equations should be able to describe this type of failure, but they were quite conservative. So we are looking into reasons for this conservatism. These physical tests are quite expensive. It took us about a year to design and test this one specimen because it's a full-scale test. So to try to investigate a bit more why there's so much conservatism for this case, we turned to finite elements modeling. So we started using software called ATENA for finite element modeling. It's not one of the more well-known softwares for reinforced concrete elements, but the thing is that it was developed specifically for reinforced concrete. The way it deals with concrete is different from any other software, and it seems to behave really well. We tend to get good results with this software. It was developed in the Czech Republic, and for quite some time now, they tend to do very well whenever there are blind prediction competitions. So we decided to use this software, and there's just a couple aspects of the software I wanted to highlight for you. First, the mathematical formulation for this finite element software is very standard. There's nothing too noteworthy about it. What makes it different is the material model, how it describes concrete, and specifically how it describes concrete in tension. One of the initial basic assumptions when designing with concrete, you start off by assuming concrete has no tensile capacity. And that is usually a conservative simplification, and the results are good enough to work with. But for anchors, when you anchor something into concrete, it's really the tensile capacity of concrete that holds anchors in place. If you were to ignore the tensile capacity of concrete, anchors would just be falling out of the walls, but they don't. So the tensile capacity of concrete is what we're really interested in. The technical term for this model is that it's an orthotropic smeared crack formulation with a crack band model. And there's a few aspects about it I wanted to highlight. First is the exponential softening. So when you load concrete in tension, it usually follows an elastic curve up until you reach the maximum tensile stress. And after that point, you get a crack that forms, but it's not a sudden drop in capacity. There is an exponential softening as you slowly drop in the stress. And so that's the diagram I'm showing here over the right. This is the stress along the crack in the vertical axis, and then in the y-axis, I'm showing the crack width. So as the crack opens, the stress drops slowly, it drops exponentially. And the shape of this drop is really important for modeling anchors, specifically the area under the curve, this G sub F, which we call fracture energy. So that was really important for us. How does this model deal with tensile concrete? And the second thing I wanted to highlight is that in this model, if you can see in this example of a beam on the top right, you only get one crack per element. You can see it a bit better towards this support. And that one crack is meant to describe all the cracking that could be happening in that one element. So this crack opening law down here is not necessarily describing a single crack, but all the possible cracks you could get along that element. So we decided to use this software and build up a finite element model of our connection, to try to run some parametric studies and understand the behavior of these connections a little bit better. And we had to start off by calibrating this model. Just to define the concrete material, there are over 20 parameters that must be calibrated. There are different ways you could try to model the anchor itself. You could think of it as just a 1D element that just carries tension, or you could try to model the full D anchor itself. There are also different contacts between the concrete and the steel. So how does the anchor interact with the concrete? Also, how does the base plate, as it pushes down on the concrete, how is that contact defined? So in order to get all these aspects right, we used a lot of physical data to calibrate our models. We had a lot of single anchor tests. Then we moved on to the groups of anchors. And finally, we calibrated the moment transfer test, the original experiment I showed you at the beginning. So to quickly run through those, we had a lot of, there's been a lot of tests done for single anchors. These tests, you would have a single anchor in the middle, cast into some concrete slab. You would have a support ring around, which you can see on the right side, and then some actuator pulling up on the anchor. A lot of these tests have been done mainly for short embedment depth, so short anchors, maybe 5 or 6 centimeters long. There's not that much data for deep anchors. In my test, the anchors were something like 35, 40 centimeters deep. So we found the deepest anchor tests we could find, which were still closer to 10 centimeters. But we decided, let me go back one slide. And with this data, what we did was create a finite element model to try to simulate this experiment. This experiment is symmetric in the x and the y direction, so we only need to model a quarter of it because each quarter behave exactly the same. So that's what I'm showing here. If you focus on the left, this is a quarter of the specimen. The steel anchor is placed here in the middle. It's being pulled up, and out here you should see the outline of the ring support, which is holding it down. And the colors on this diagram on the left are showing basically the width of the crack as it opens up. So the cracks originate at the anchor head, which is here. I think in this image I turned off the steel material so we could see the concrete better, but the anchor is placed right here in this corner. And you can see the cracks as they propagate towards the surface form a cone shape. And if this video should work. You can see where the cracks originate at the head and shoot up towards the surface as we load. On the right, I'm showing the tensile stresses. So the redder means the higher the tension stress. And what you can see in this diagram is that as the crack opens, the stresses start to drop along that crack. So that means that the crack has opened, and not only did we see the crack open, but it opened so far that there are no longer stresses traveling across that plane, because remember that we have the exponential softening after you reach the peak stress. And when you're using this type of software, one of the first things you need to look at is the crack patterns. Do the crack patterns make sense? This will be the first thing that you will see is wrong if you've defined something incorrectly in these models. And so when we got these cone shape failures, we knew we were on track. And once we had these crack patterns behaving correctly, now it makes sense to move on and look at the load displacement curves. So I'll show you that right now. So these two diagrams show in gray some experimental results from single anchor tests. I wanted to highlight here on the left, even though these are 4 physical tests of anchors, identical anchors placed in the same concrete, there's quite a lot of variation in the peak strength. So this one up here has failed at about 120 kilonewtons, this one down here at about 100. So there's about a 20% variation in the strengths of these anchors. And this is experimental data, so it's challenging to try to calibrate a finite element model to a phenomenon that's quite variable itself. To try to get this spread of the data and understand it a bit better, and all the diagrams I'm going to show you, we ran multiple finite element models, be it with, in this case, we ran different mesh sizes and slightly different concrete properties to try to get the spread of the data a little bit better. Also, even the developers of this software themselves admit that if you get your finite element results, if it's plus minus 15% compared to the physical test, that's considered a very successful model. So I just want to help make it clear the variability that you get with these types of tests. So we calibrated these models. This is one concrete mix on the left, and we have a different concrete mix on the right. But the principles that we learned from one concrete mix, we applied those directly to the other concrete mixes, and they seem to behave very well. We're pretty glad with that. So it seems like we'd found modeling principles, ways of modeling the anchor itself that behaved well, not just for one model, because it would be really frustrating if you calibrate a model for one concrete mix, you move over to another concrete mix, and you have to start from scratch. There's not much use of that. So thankfully, we found material properties that worked well across concrete types. With those lessons learned, we moved on to the calibration of some group anchor tests. These groups of anchors were actually tested here at Berkeley as well by another graduate student a few years ago. In these tests, we have our concrete slab here, and we have our anchors, which are attached from the bottom, and we're pulling down on these anchors. This model is also, or this experiment was also symmetric in the X and the Y direction. So the model we built, which I'm showing here, is also just a quarter model. Every quarter behaves exactly the same. Here I flipped it upside down. So here you can see the anchors. These are being pulled up. These green plates on the top are the reaction plates. I just wanted to stop here a second and ask you, what should the crack patterns look like? If this model works correctly, the crack patterns should make sense with the experimental data, but you should also start to get a feel of what these patterns should look like. So if I go forward one slide, on the right here you can see the crack patterns. So at first, as we loaded this model, we started to get a lot of this surface cracking. This is flexural cracking, just because we have a large slab. This flexural cracking was significant. And then at some point later on, we got this nice cone-shaped failure. So the colors are representing how wide the crack has opened. And also, these anchors are placed closely enough together that their cones, they don't form an individual cone each, they form a group cone here. And this was consistent with the experimental results, depending on the size of the screen you're looking at this on. It might be hard to see, but here on the left, we did see a lot of flexural cracking, and then we had a sudden cone failure. So now that the crack pattern makes sense, we moved over to the load displacement curve. So the gray line represents the experimental results, and then we have 4 different finite element models with different mesh sizes, slightly different concrete properties. One thing we were quite happy with the previous models and these is that we were able to match the initial stiffness, the elastic stiffness. If you can't match the initial stiffness, or if we hadn't been able to match the initial stiffness, I wouldn't trust anything after that once cracking and softening starts happening. So thankfully, we were able to match the initial stiffness very well. We had to do very little tweaking with the principles we learned from the single anchor tests moving over to the group anchors. And the peak load seems to match pretty well. Pretty happy with this. So we calibrated our models with different group anchor tests. This is just one I'm showing you. And once we did that, we were finally able to move back to the original goal, which was to model these moment transfer tests. This specimen is only symmetric in one axis, so we did have to build half of a specimen. We couldn't go all the way down to a quarter. So here I'm showing the steel and fine concrete. The pink layer is fine concrete layer because that's where we expect most of the damage, and then coarser concrete towards the ends. And if I turn off the concrete layer, you can see the rebar placement. We have a top mesh of rebar, bottom mesh, and then some hoops around the anchors. You can also see the anchors themselves are modeled as full 3D elements. So just with all the other models, the first thing we need to look at is the crack patterns. Do these make sense or not? So here I'm showing 2 cross sections of the specimen, and I'm showing different mesh sizes. So a pretty coarse mesh on top and a finer mesh on the bottom. So as we load to the left, the anchor group on the right is loaded in tension, and we get this clean cone failure mode. for both the coarse meshes and the fine meshes. This is consistent with our experimental results. So then we moved on to the load displacement curves. Here in gray, I'm showing the experimental results. There's a light gray and a dark gray because we had an east anchor group and a west anchor group as we loaded this column cyclically. And the x-axis, I'm showing the column drift ratio, and in the y-axis, I'm showing the force in the anchors as we were cycling it back and forth. The finite element model we ran is just monotonic loading. We're just pushing on this. It already takes a day or two to run one of these models. So cyclic models, we have run some of those, but they take forever to run. So we decided to run parametric studies with these monotonic loading tests. So they should behave as a type of envelope. So we are quite happy with these results. I'm showing 3 different models with 3 different mesh sizes. So that was part 2 of the presentation, the calibration process. And we spent a lot of time trying to calibrate these models because right now we're moving into parametric studies. I'm going to use this model to investigate some other type of geometry. And really what we're doing is extrapolating. You have to be very careful when you extrapolate without physical data. We're basing ourselves on a physical test, but we're extrapolating out from there. So in order to build the most robust model we could, that's why we went through the long process of calibrating our model with lots of single anchor tests, group anchors, and moment tests to try to build a model that's robust enough to try to extrapolate a bit. And this is the part of the research that I'm working on right now. I'm using these parametric studies to investigate how can we improve these connections? How can we improve the breakout equations? Why did they seem so conservative? One of the most interesting or promising aspects about these connections is slab shear reinforcement. These specimen we tested had no shear reinforcement. It looks like the model on the left. We had a mesh on top, a mesh on the bottom, and hoops. But what if we add shear reinforcement to this slab? There's another research project going on here at Berkeley looking at all the benefits to adding shear reinforcement to foundation slabs, and it's becoming more common, especially for very tall buildings. So on a construction site, at least here in the US, they call them candy cane bars. You have these bars with a 180-degree hook on top, head on the bottom, and during the construction process, once the top mesh is in place, you can just come by and drop these candy cane bars and hook them onto the top reinforcing so they just hang in place. So this is something that's already done in some buildings. So our question was, what will that increase the strength of your column foundation connections? So we ran different models with different amounts of reinforcing. This model here in the middle, we have about 0.078% of reinforcing. That's just the area of the rebar divided by its tributary concrete area. And once again, let's look at the crack patterns. What happens with cracks when you add shear reinforcing? So on the left, I'm showing the original model with no shear reinforcing. As we load the column to the left, we get our cone failure mode, which I've already shown a couple times. On the right, I'm showing the model that has a high amount of shear reinforcing at the same load as the one on the left. So you can see that they're both loaded to the same load. The one on the left has failed, has no shear reinforcement. The one on the right is barely cracked. If we continue loading the one on the right, we do eventually get a cone type failure, but at a much higher load. This also makes sense with some of the few tests that have been run on how anchors and rebar interact. And different researchers have found that when you add rebar to these connections, the shape of the cone changes. Instead of having a very wide open cone, you get this much steeper, shallower cones. So these crack patterns seem to make sense. If we look at the load displacement curves, Again, I'm showing experimental results in gray, and these two yellow lines are the two models we calibrated with no shear reinforcement. But if we then add a little bit of shear reinforcement, this corresponds to minimum slab shear reinforcement. We get a boost in strength, and then you could add quite a bit more and have a much higher strength here. One thing to note is that this dotted line up towards the top is the strength that was predicted by the beam column joint equations right from the beginning, when I showed you that the beam column joint equations seem to show a much higher strength than what was observed experimentally. It looks like if we add enough shear reinforcement in, it boosts the breakout strength, so much so that the failure mode changes. We stop getting clear cones and we start getting joint failures. I'll show that here in the next slide. We ran many different models with mesh sizes and different amounts of shear reinforcing and different rebar sizes. And you can summarize the results into this graph. In the x-axis, I'm showing the amount of shear reinforcing. And in the y-axis is the strength boost that we saw due to the shear reinforcing. So we have no shear reinforcing, our results are around 1, there's no strength gain. But if you add 0.3% shear reinforcing, the models show 50% gain in strength, which is quite significant, especially compared to all the other ways that we investigated how to improve these connections. This one seems to be the most promising. This dotted vertical line is showing minimum slab shear reinforcement. So even if you add the minimum shear reinforcement, you might even get up to a 20% boost in strength, which is still quite significant. So this is the trend that our models show. What we want to do now is test this in the lab to see if with some experimental data we can corroborate these results, because this graph is made purely from simulations and we need some physical tests. So if we weren't on lockdown, I would be in the lab right now building the specimen. Probably it would fit right here, so about 0.3% of shear reinforcing, to try to see if we can match this data. We've been on, this is our 5th week on lockdown. The campus has been shut down, so we're waiting to see when we'll be allowed back on campus. So whenever that happens, I'll be rushing back to build this specimen and get some data to try to corroborate these results. Another aspect that we found interesting is where you need to place the shear reinforcing. In all the models I'm showing here, shear reinforcing was placed along the whole slab. But we noticed that only the bars near the connection really participate. You can actually remove the shear reinforcing that's far away and it has no effect. And so the sweet spot seems to be about 1.7 times the length of the anchor. So if you place shear reinforcing in that area, our models say that you should get a significant boost in strength. So this is still a work in progress. Hopefully in a couple months we'll be able to get some physical data points to add to this diagram. But so far it seems promising. Here I'm highlighting that in this region, when you start adding a lot of shear reinforcement, I mentioned earlier, the cone failure mode becomes less and less evident. And what you start getting is crushing of concrete in that region. So one way to interpret these results is that maybe for these column foundations, we should be checking both failure modes. We should check joint failure modes and the cone failure modes, and the minimum is the one that governs. So that's the theory, at least. We're looking into it to see if that makes sense. But so far, that's what we believe is happening here. And hopefully we'll be able to improve the breakout equations by including some factor that considers shear reinforcing. There's one other effect that might be why these results were so conservative, and that is the base plate compressive force. And this is my last slide, by the way. So if you have a base plate with anchor groups on each side, you'll have a tensile and a compressive force. If this compressive force is close, it might push down on this anchor cone and increase the strength that you get from this cone failure. If this compressive force were, say, way out here to the right, then you wouldn't expect a boost in strength. That compressive force is too far away. So this might be one of the things that gave our experiment a boost in strength, and that's something the code doesn't consider. Neither the American code nor the New Zealand code have this factor in it, but the Euro codes do, in fact. So I'm showing some of these diagrams of the different factors that have been proposed. The one highlighted in orange is the one used currently in the Euro code, and in the x-axis, it's basically showing you the joint aspect ratio. It's simply telling you, where does that compressive force fall? Does it push down on the cone or not? And in the vertical axis, you see the strength boost that you get from this connection. So one of the other specimens we hope to build whenever we're allowed back on campus would be something that would fall somewhere here in this diagram, somewhere around 0.75 joint aspect ratio. So that would be a tall, slender joint with deeper anchors to see if we really do get this boost in strength. Again, a lot of these tests were run for very shallow anchors, and so we do need to see how do deep, large anchors behave. Do these trends still hold? But hopefully we'll be able to get back into the lab, get these tests ready. And who knows, maybe suggest to the committees that maybe these factors are important and should be included in our design codes. Might be able to understand better how these failure modes happen and not kind of pick whichever method I like, which seems to be what's happening nowadays. So I said that was my last slide, so thank you very much for taking time out to watch this presentation. I hope it was interesting. Wanted to acknowledge some of the sponsors here. And yeah, we'll be open for questions if there's anything you'd like to hear more about. I'd be glad to answer any questions.
Thank you very much, Benjamin, for your presentation. Extremely interesting. I just want to open the QA session. If you click on your chat tab, that is at the bottom of your screen, you have a meeting chat, and you can type in your questions.
Yeah, so we were just about to start building this new specimen when the university shut down. I'm almost thankful we didn't start, because if we had, we'd have concrete in the lab, hardening, getting stronger and stronger, and we wouldn't be able to test it.
So too strong, yeah, okay.
A couple weeks later, and we might have had some trouble.
Yeah, that's right. Very, very interesting presentation. So when you mentioned, I've seen that you had this lab, and of course your bending moment is part of the picture. Did you also test specimens more chunky, where maybe it's like a big plinth with maybe effect of the edge of the plinth instead of having a huge slab with a bending moment?
Mm-hmm. Yeah, so initially we were considering testing that and looking at edge effects as well, because not all columns will be able to be, like you say, in the middle of the slab with lots of chunky concrete around it. But the more we looked into this, we saw that there's, even for the simple case of a column anchored in chunky concrete, there's still a lot of uncertainty. So we decided to start off with that problem. So no, we haven't tested the effect of having columns close to edges, but that's one of the things we want to look into now that we have these finite element models that have been calibrated.
Yeah.
And another thing to point out is that most tests that have been done for these types of anchors have been done on really small anchors. I alluded to it a couple times during the presentation. Most equations are done for, I don't know, 6, 7 centimeter deep anchors, but a lot of the anchors we build are much, much deeper than that. And we do know that the trends don't necessarily follow those trends very easily. So we're looking into that. How do deep anchors behave compared to these shallow ones?
Mm-hmm. Yeah, because one of the questions, so for example, here in New Zealand, 3101 doesn't have guidance for when you combine the strength that you get from the head anchorage with the development length along the bar. In your case, this was, of course, with metric bars, so it's a bit different. But if you have the reinforcement bars, with the ACI and also with the Australian standards, you have provisions of how to combine the development length that you have along the deformations and with the headed anchorage. So that's interesting. It would be interesting to see test data on that too.
Yeah, that's right. The current anchoring equations assume that you're placing an anchor in plain concrete. It has no reinforcement in it whatsoever.
Yes.
And intuitively, it makes sense. If you add reinforcement to it, you should see a boost in strength. But we don't have any models to tell us if you add this reinforcement, you get this boost in strength. So that's what we're trying to work on, trying to get a grasp of how that behaves.
We have a question in the chat. Would any future testing consider casting bolts with an annulus? Would you see this as increasing strength?
I honestly don't know what an annulus is. So what do you mean by that?
Yeah, I don't know either.
We might have a different word for it here.
Yeah, unfortunately, English is not my first language, so probably. Like a cast-in disc.
Yeah. Oh, yeah. Actually, we did run some of those tests. So the size of the head of the anchor seems to be very important. The cracks originate at the head of the anchor and then shoot up towards the surface. So the size of the head is really important. So we ran a couple tests with very small heads. Small head meaning that the bearing stress on the anchor might be something like 15 F prime C, something like that. Because it's very confined concrete, it can get all the way up there. And then we also ran some tests where we had 2 nuts and then added a plate to make it bigger and distribute those stresses more. And we did see a boost in strength there. Again, there's no code equation that will tell you how big a head will give you what boost in strength, but it is a trend that a lot of tests seem to show. I think that's what you meant. I hope so.
Yeah, I think so. There is thank you. Okay. Yeah, it is. Just answer.
Okay, perfect.
Yeah, thank you. Also interesting, you have another question? Yes. Do you have a target for completing the research?
You mean time-wise? Well, right now,
yeah, it would be interesting.
Originally, I'm planning to graduate in May of next year.
Time-wise, yes, time-wise.
Yeah, we'll see how that goes. Or, I don't know, whenever we're allowed back in the lab, maybe 6 months from then, we would have the first test, and 6 months after that, the second test. We'll have to see. I have that question myself.
So also interesting your shear reinforcement. It's kind of like the punching shear studs.
Yeah. Yeah, it's actually very similar. There was another set of tests that were done looking at the difference between punching shear and breakout. So if you have your slab and you anchor your column in there, if your column is in tension, it'll rip out a cone. But what if you push down on the slab? You could eventually punch through the slab. And you might expect those two failure modes to give you similar loads because the crack patterns are almost identical, just pulling or pushing. But the equations give very different results. So that's also being looked at here.
Yeah. We have another couple of questions, one from Enrique. Have you or are you going to consider post-install anchors, mainly chemical?
So far, no. We're looking just at cast-in-place headed anchors. The load transfer mechanisms are very, very different. That it's almost like starting from scratch if you move from one type of anchor to another, because the post-installed transfer load all along the shaft.
It's with a bond strength. Yeah.
Right at the head.
Yeah.
So currently, I'm not looking into post-installed anchors.
And also a question from Shouting. In Strut-and-tie model that you've done for the column and slab joint test that you showed at the beginning, was it just based on anchors and concrete only? Have you considered the reinforcement in the Strut-and-tie model? Thank you. I think.
Yeah, I showed a very simple version of that Strut-and-tie model. Let me bring it up. Okay, it should be here on the screen. So in this tie model, we have the tie here, the anchors, the compression strut. I'm only showing those two here just for simplicity, but we also considered the horizontal force that will be carried by the top and the bottom bars. Also, these hoops help to hold the joint together. So yeah, we included the effect of all those reinforcing bars to calculate the strength. The limiting factor for this one, if I bring back the diagram that shows you that the Strut-and-tie model had very low strength. The limiting factor was actually the head of the anchor. The anchor head is so small that this diagonal strut has to concentrate all its force down into this very small area. And that's what would limit the strength of the connection. So it would be interesting to see, add in the annulus, as you call it, or add in some plates. Well, what happens if we add in a larger plate? Maybe Strut-and-tie model might be more useful in that case.
Yeah. Okay. I think if we don't have other questions, we can close the presentation. And thank you again very much, Ben, for the extremely interesting presentation. And thank you for all the participants with this new means of reaching out to Open Structural Group members. And I hope we'll be able to have another presentation as usual. But yeah, we'll see how it goes with a COVID-19. It's nice to be prepared to have this kind of tools to meet each other also remotely. So hope we will see all together next time within a month, possibly at the university. Thank you.
Thank you.